Now we are going to look at two-source interference. The definition for interference will be referring to the phenomenon of two or more waves of the same type meeting at a point in space to produce a resultant wave disturbance that is given by the superposition of individual waves at that point. So interference simply means two or more waves meeting at a point, and of course the two waves must be of the same type. For A level we only do when two waves meet. If you look at this picture, you can see that the gap between the rocks actually acts like an aperture, so there is spreading of the wave here. Similarly here also, okay, there's spreading of the wave. Here you see a bit, the gap is small, so more spreading, and so far so on. So when this part of the wave spread and this one spread, there will be interference. So what we see over here are actually interference of the waves coming from these two sides. Okay, in lecture I did a demo on interference of light. So the setup looked like this. I have a laser beam, which is only one beam. Okay, so if I don't have the two slits, right, what you see on the screen will be just one spot. So in order to have interference, I need two beams of light. And to do that, instead of using two lasers, I'm going to use a double slits. Okay, a double slits basically consists of okay, this one, it can be like a card with two openings. Okay, so the light will pass through the slit called S1, another slit S2. So it acts like there will be two beams of light, and there will be interference pattern. It will spread and then they will interfere. At the point whereby you have constructive interference, that is the crest and the crest meet, there will be a bright spot. Okay, then some other spots here, probably there will be a point where the crest and the trough meet, and when that happens, you have destructive interference, so you see dark spot. Okay, so when I did the demo, you saw that it consists of bright, dark, bright, dark, bright, dark region. So instead of just seeing one spot of light, you are seeing many spots. Okay, this is due to the interference of light. This is a more detailed diagram that is given to you in your lecture notes. If I'm not using laser, take a look at this. If the light source is any other light source, I will need another third slit, sometimes we call it extra slit, to be placed in front of the light source. Okay, the reason is because we need the light going to S1 and S2 to be coherent. So we need to limit the amount of light. So the purpose of this slit, the third slit, is to act as a is to filter out, is to ensure that the light going to S1 and S2 are coherent. Okay, then we have spreading of the light from coming out from S1, so you can see the diffraction pattern here. Similarly, diffraction pattern for the lights coming from S2. So there will be interference. At the point where the crest and the crest meet, like all this point here, you have constructive interference. So if you put your screen here, you see a bright spot. Okay, similarly, all these points here will be constructive interference also, because that's where the crest and the crest meet. Then somewhere in the middle of the two-way front, okay, somewhere here, this is where you have the trough. So if you have the trough and the crest meet, that is where you will have destructive interference. So all this point here. That's why these spots here you see dark. This experiment is known as the Young's double slit experiment. Thomas Young actually performed this experiment some 200 years ago, and he managed to measure the distance between the bright spots, measure the distance between the slits. Okay, these two slits. Measure the distance between the screen and the double slits, and from there he could calculate the wavelength of the light. Okay, the third demo that I actually performed in the lecture was on sound wave, but the explanation is similar to light wave. So I will need two sources here. I use a signal generator from my laptop, connect it to the loudspeaker. Okay, so imagine if you have two loudspeakers, each of them will have their own diffraction pattern, and when they interfere, I will have a region of constructive and destructive interference. Depending on where you are positioned, say a student is positioned at the point P, you can see that the crest and the crest of the other sound wave actually meet. So if a student is positioned at point P, we have constructive interference, and the student will hear a loud sound. How about a student at the point Q? Will he or she hear a loud or a soft sound? Well, if you look at the point point Q, it is where the crest, okay, the dotted curve, right, represent the trough, it is where the trough and the trough meet. So when you have trough and trough meet, again you have constructive interference. So you should you should hear a loud sound. Then if I have a student at position R, you can see it is the crest and the trough meet. So when this happens, there will be cancellation. This is destructive interference. Okay, now we will discuss the conditions for you to get interference patterns that are fixed. So fixed interference patterns are known as steady observable interference pattern. When it's observable, that means the regions of high and low intensity should stay at the same position. It shouldn't be fluctuating. Interference fringes, the fringes refer to the region of high intensity and low intensity. So at the high intensity side, we call it the bright or the high intensity fringes. Okay, the first condition is the two waves must be coherent, meaning they must have a constant phase difference. So the two waves need not be in the same phase, but the phase difference must maintain. So for that to happen, the two waves must have the same frequency and the same wavelength. If we are referring to transverse wave, the two waves must be unpolarized, or they must be polarized in the same plane, so that we can have constructive and destructive interference. More of destructive interference. Imagine if they are not polarized in the same plane, then there will never be complete cancellation of the waves. Oh, there's one more third condition, that is the two waves must be approximately of the same wavelength. Why? Because in order to have destructive interference, we need the two waves to cancel each other. Okay, now I move on to condition for constructive interference. We have been talking about constructive interference, that is where the crest and the crest meet. So what is it beside crest and crest meet that we get constructive interference? The definition for constructive interference will be where the two waves meet in phase. Okay, when this happens, they reinforce each other. So if you look at the diagram here, notice that at this point of the time, at this instant, the two waves, they meet in phase. It is actually the equilibrium, and the equilibrium of the two waves meet. So when this happens, you will have constructive interference because the two waves are at the same phase. Sometime later, say a quarter T later, you notice that the trough and the trough meet. So the total displacement will be doubled. Okay, the amplitude will be doubled. So the intensity, which is proportional to amplitude squared, will be the highest. So we do have maximum amplitude, and then go to 0 at half T later, go to maximum 3/4 T later, and so far so on. So at the point whereby we have constructive interference, the intensity of the source actually, the intensity of the spot actually varies from 0 to maximum, and then back to 0 again. But because the fluctuation is so fast, we will not be able to observe it. So what we see on the screen, like what you saw in the LT, will be just bright spot throughout, but actually it's changing, just that we can't, our eyes are not fast enough to pick it up. Similarly, when we are doing the sound, at the same position, the intensity is fluctuating from 0 to maximum, but because the frequency is so fast, I think I used a frequency of 800 Hertz, okay, changing 800 times per second, our ear again is not able to pick up. Okay, so although it's constructive interference, it doesn't mean that it's always crest and crest meet. Then we would like to form an equation for the path difference. Path difference simply means the difference in the distance between the two waves. Say I have a point P where the two waves S1 and S2 meet. The wave S1 will have to travel a distance of 2 lambda, and the wave S2 will have to travel a distance of 3 lambda. So the path difference, which is S2P 3 lambda minus S1P 2 lambda, will be equals to 1 lambda. And when the path difference is a whole number of wavelengths, we get constructive interference. Condition for destructive interference, well, that will be when the two waves meet exactly out of phase. Exactly out of phase means 180 degrees out of phase. They will cancel each other. So the path difference in this case, right, will be equals to a half lambda, as shown in the diagram here, or it could be 1.5, 2.5, and so far so on. So beside the path difference, we would like to also obtain the condition for the phase difference. The phase difference, if I recall the formula, sub in the path difference, the symbol for path difference is delta x. Okay, this is the phase difference. If I sub in the path difference for constructive interference, which is n lambda, I substitute in here. The equation for phase difference, right, will be 2n pi for constructive interference. Similarly, if I sub in a path difference of n plus half lambda for destructive interference, I'll get the phase difference of 2n plus 1 pi for destructive interference. Okay, with that we are done. We move on to example 5. Okay, I would like you to try this question. You take 5 minutes to do it. Okay, assuming 5 minutes up, let's go through the question. An interference experiment is set up using two identical coherent sources of 1 cm width. So that is the wavelength. The diagram below shows to scale the position of the sources P1 and P2 and of 5 observation stations A to E. Which station will be at a position corresponding to a constructive interference? Okay, the diagram is drawn to scale as mentioned in the question. So the information that I can get will be the path difference. So in order to get a constructive interference, the path difference must be a whole number of wavelengths. So it could be 0, 1 lambda, 2 lambda, and so far so on. So I will have to calculate the path difference from the from the two sources to the station. So after calculating, notice that only station C give me a path difference that is n lambda. Okay, the rest do not. So only station C will give me constructive interference. Okay, we move on to experiments on two-source interference. The first experiment which you have seen is the Young double slit experiment. Okay, before this there's another one, but I think it's water waves. Okay, that one is similar. Whether it's water waves, sound waves, or light waves, the discussion will be similar. Okay, so you have diffraction pattern and then you have interference pattern. But what I like to highlight here will be the fringes that you see on the screen. Okay, remember we say when you have constructive interference, you see a bright spot, you have the crest and the crest meet. So this point O here, which is equidistant from S1 and S2, will give me a path difference of 0. That's why we call this 0 order. And similarly, okay, this point here, this is called the first order maximum because this point corresponds to a path difference of 1 lambda. And you will have guessed This point here, okay, the bright spot, is called second order because it corresponds to a path difference of 2 lambda, and so forth so on. So on the other side of the screen, you also have first order maximum, second order maximum. Right in the middle, right, is where you see dark spot. We also name them. There isn't a central dark spot. Okay, central is bright spot because you have constructive interference. Then if you move up, this will be the first order dark spot. Then you have the second order dark spot, and so far so on. Okay, the next thing we are going to derive the equation for the fringe separation, or the distance between the central bright fringe to the end of the bright fringe. To do that, right, we need to look at Young double slit experiment. Okay, we have the 2 slits, S1, S2. So 2 waves will be coming from S1, S2 to the point P. Okay, so one from S1 to the point P, another from S2 to point P. Point P is the nth order bright fringe. It could be first order, second order, and so far so on. I would like you to focus on this green triangle, okay, which is formed by S1, S2, and A. The distance from S1 to S2 is called small d. Okay, this is called the slit separation. Small d is very small, typical of the order of 0.1 mm to 0.9 mm, fraction of an mm. Okay, if I were to drop a line down from S1 to A, S2A will give me the path difference. We are assuming that S2P and S1P, they are almost parallel. Okay, because the 2 slits are so close together, fraction of an mm, so the 2 waves are almost parallel. The big D, right, later I'll mention, is very far, is very big compared to the small d. That's why big D, small d. Okay, if I were to drop a line from S1 down, perpendicularly down to S2P, S2A will give me the path difference. And the path difference must be n lambda because at point P you have constructive interference. Then, if I let the angle theta here be between I let S2, S1A, this angle here be theta, then sine theta will be the opposite, which is n lambda divided by d, where d is the hypo. Okay, next I'm going to consider another triangle, which is this blue triangle here, PBO. Then tangent theta, okay, these two angles are approximately the same because the angle is very small. Okay, so I'm going to call this angle theta also. So tangent theta will be equal to the opposite, which is yn divided by the big D. Okay, I mentioned that the angle is very small, so using small angle approximation, sine theta will be approximately equal to tangent theta, which is approximately theta. So I'm going to equate, okay, n lambda over d to be approximately equals to yn over d. So from there we derive the equation for yn, which is the distance from the central bright fringe to the end of the bright fringe. If you are referring to the first order bright fringe, then your n will be 1. If you are referring to the fifth order bright fringe, then your n will be 5, and so far so on. Okay, with that we come to an end of the second lecture.